Hello, everyone. I would like to share some progress on the Mnesia asynchronous replication project. So I tried to put together this presentation in a way that hopefully explains why it's beneficial, even for people who are not very familiar with technical stuff. So let's get started. First, I want to share some background. What is Mnesia? How does EMQ X use it? And why it's beneficial to work on the performance improvement. So Mnesia is an embedded distributed database that comes included with Rlog. EMQ X uses it to store the following data. It's runtime data such as MQTT topics, subscribers, and routes, configuration. Also some plugins store data in Mnesia, for example, ACLs, user authentication, and so on. So how does Mnesia transaction model work? In Mnesia, every table replica is equal, and Mnesia uses a full mesh peer-to-peer model to replicate transactions between the replicas. And Mnesia is an ACL database, so it has some rather good consistency guarantees. Mnesia uses Rlog distribution protocol for data replication and transaction coordination. And to summarize on the high level how it works, let's consider these two diagrams. So TX is a transaction process, and A and B are Rlog nodes that hold the replicas of a table. Suppose transaction tries to write some data to the table on some key. In order to do this, first, the transaction process has to send messages to every node that holds the replica of a table, so to A and B. And the replicas check Mnesia worker process data to see if this lock is held by our transaction, and depending on the outcome, they can either add this new transaction to the waiting queue, or reply with OK, or ask transaction to restart. Suppose the transaction was able to grab all the logs, we get OK, and we try to commit the transaction. So again, the transaction process has to negotiate with every node in the network. Suppose everything goes fine, we receive OK, transaction commits, it does some other stuff, and finally it sends messages to release the logs, again to each and every node. And if there were 3 nodes, the transaction process would have to talk to 3 nodes, etc. So where lies the problem with Mnesia? This full mesh model is very susceptible to network partition. Basically, it needs to have 2 squared links between nodes operational. And also transaction latency tends to grow with the number of nodes, because the amount of communication that has to be done also grows. In the last demo, I showed this small graph from the benchmark, which shows how transaction latency grows with number of nodes. And yeah, clearly there is some tendency to grow. So to briefly check what is our solution to this problem. We want to introduce a different kind of Mnesia node, so-called replicant node, that does not participate in the transaction negotiation process. It just passively replicates transaction from the regular Mnesia node, which we call core nodes. So basically, we will run application EMQ X on these replicant nodes, and we can scale the amount of these replicant nodes, but we won't hold any logs. We won't block transactions, and they will have a local replica of data. So read-only transaction will be able to use this local data. So the number of these replicant nodes won't affect the write throughput of Mnesia. On the last sprint, I showed some benchmark result that basically justify this hypothesis that we can use, that we can make a rather huge gain in throughput by using this model. I think everyone was present, so I won't go into details of this graph. And finally, I will start sharing what has been done in the last sprint. Quite a lot, actually. First of all, we finished implementation of replicant state machine. So it means the replicant nodes can now restart from failure, and we can add and remove the replicants from the cluster dynamically. Another big thing is that now shard configuration is done using the same kind of annotation that EK uses to configure tables. So if you add the following annotation to the module, during startup, EK will look for this annotation. It will create shard tables on the core nodes. It will start all the processes on core and replicant nodes, and finally it will create a filter for the transaction log entries to dig for the operations that belong to the shard. And finally, we created the APIs for initiating read-write transaction and read-only transaction on the core and replicant nodes. I will demonstrate them. And we've started implementing fault-tolerant tests. Created a test case where replication is happening during all the stages of replicant startup, and a new test case which inject random crashes into the system. Okay, let's move on to the live demo. So first, I'm going to start a cluster with 3 nodes. One of the nodes is replicant, and another is, and 2 other nodes are core nodes. I will start console on both core and replicant nodes and check the roles. I will move this for now. So this is the core node. And let's check how schema for our test table looks like. As you can see, only 2 nodes have RAM copies on this table, and so it doesn't have these copies. Okay, whatever. And let's run the same command on the replicant nodes. As you can see, it only has RAM copies on this very same node. So we are not using Mnesia replication to copy the data. But let's run some transactions on the core node. And let's check, indeed, this transaction has been replicated to the replicant node. We can also run the same function on the replicant nodes. Let's change some value to 5, for example. And let's run a read on the transaction on the core node to see that the data was replicated where, yeah, indeed, as you can see, the value became 5. So now let's check that even if we stop the replica and run some transaction on the core node, the data will be still so replicated to the replica. So we change the value of our key to 6. Now let us restart the replicant. And yeah, after it starts, we read this value, and as you can see, it became 6. So everything works. So plans for the next sprint. There are going to be 2 tracks of work, performance and consistency. I'm planning to move on from synthetic tests and start integrating patch ticket to EMQ X. And for consistency track, I'm going to add more common tests and start investigating Jepsen test suite. That's it. Any questions?
Is the Jepsen test suite for the database, right?
Yeah, it's an open source test suite for databases.
No, okay.
Hello, Dimitri. How to handle net split?
So net split is going to be handled on the core node. It will be handled as with Mnesia. Nothing changes except probability of the net split is hopefully going to become less. And on the replicant node, net split is not as big of a problem, because if replicant loses connection to the core node, it's going to reconnect to one of the core nodes. And if, yeah, that's basically it.
Great. Thank you, Dimitri, for the demo. For the context, we have EIP document. I forgot the number. What is it? Dimitri, do you remember?
I think number is 4.
Yeah. EIP document 0004 is the change proposal for this async replication implementation. I will share the link with the video later. And the application which has this implemented is called EKKA, as Dmitry just demoed. I will also put the link there for the references. If there's not any more questions, let's move on to William.